Good morning, students. Now we are going to the class 4 in the ring theory and vector calculus, that is mathematics paper 5 of final BSc AKNU 5th semester for the academic year 2020-21. Now we are discussing first unit, that is rings 1 class 4. In the previous classes, we have discussed the definitions and we have learned the definitions. Integral domain, I already told you that all of you want to learn these definitions very well because these are useful to the entire syllabus. That means I am repeating, that's why I am repeating this again, that what is integral domain? An integral domain, an non-empty set R with respect to two binary operations plus and dot is called integral domain if it satisfies the two conditions, that is R plus dot is abelian ring and the second one is R has no zero divisors. Next one is field. A non-empty set R with respect to two binary operations plus and dot is called field if it satisfies three conditions. The first one is R plus dot is abelian ring and the second one is R has unit element. The third one is every non-zero element in R has multiplicative inverse in R. Okay, right. Now we are going to the important theorem, that is theorem 4. Every field is integral domain. Or it may ask in the university in the other form, university question paper in the other form is a field has no zero divisors. Or there may be another form is there, that is the third form, that is an abelian division ring has no zero divisors. We have already previously discussed that an abelian division ring is a field. Abelian division ring means field. Field replaces with abelian division ring. If you observe these two statements, what is the main difference? Field, abelian division ring. These are the two differences. Abelian division ring is equal to field. Okay, understand? That's why an abelian division ring has no zero divisors means a field has no zero divisors means the same. Okay, right. What is every field is an integral domain? It's a direct question. Every field is integral domain. For that, we must understand the definition of field and the integral domain. If we prove this theorem only if we understand the definition of field and integral domain only. I am another time going to the back. Before that, I am taking that we have to take a field and we want to prove that field is an integral domain. For that, I am taking, suppose R plus dot is field. We prove that R is an integral domain. Every field is an integral domain means I am taking R is a field. I am prove that R is an integral domain. Okay. Okay. Integral domain means what is the definition of integral domain? R is abelian ring. R has no zero divisors. We want to prove these two bits. We have taken field. Field means these three bits are satisfying. What is the first bit? R plus dot is abelian ring. This was the same as the first one also of the integral domain. Is it right? That means we don't want to prove the first bit of the integral domain because it was already in the field. Field in the field, R plus dot abelian ring, that means the first bit is clear. So we wrote here, for that we prove that we want to prove R is integral domain. For that, R is a field means R is an abelian ring. That's why integral domain two bits, the first bit is not we don't want to prove it because it is a field. In that field it also is there. That's why we prove the second bit, that is R has no zero divisors. It is enough to prove that R is an integral domain, that R has no zero divisors is enough. Now for that one, I am taking A is a non-zero element and B is an element in R. We know that A is a non-zero element in R. R is field. What is the definition of the field? The third bit in the definition of field is every non-zero element in R has multiplicative inverse. In the field definition, the third bit is every non-zero element in R has multiplicative inverse. This is the condition. I am writing this condition as it is in that theorem. For A is not equal to 0 belongs to R. There exists A inverse belongs to R such that A inverse is equal to A inverse A is equal to 1. Let it be 1. Now I am taking AB is equal to 0. We want to prove R has no 0 divisors. That means if we take an AB equal to 0, then we want to prove that either A equal to 0 or B equal to 0. Then only we say that R has no 0 divisors. Okay, right, I am taking AB equal to 0. We know that A is a non-zero. A is not equal to 0. We want to prove any of these one. That means either A equal to 0 or B equal to 0. But here A is not equal to 0. That means we must prove B is equal to 0. For that, A inverse is in R. So I am multiplying both sides with A inverse. A inverse into AB is equal to A inverse into 0. Okay. I am using the associative law. By associative law, A inverse into AB becomes A inverse A into B. And RHS what? A inverse into 0 is 0. Right. What about A inverse A? A inverse A. What about A inverse A? From 1. A inverse A is 1. A inverse A replaces with 1 and B is as it is, 0 is as it is. 1 into B is B because 1 is the unit element. B is equal to 0. We got B is equal to 0. AB equal, we have taken AB equal to 0 and A is not equal to 0. That means we prove that B equal to 0. Therefore, R has no 0 divisors. That means R is integral domain. We have taken R is field and that is R is integral domain. Okay, right. Next we go to the another theorem. That means converse of this theorem. What is the theorem for? Every field is integral domain. I am asking that is integral. If we take an integral domain, then is maybe a field? No, it is not possible. That's what I am writing that. Every integral domain may not be a field. Always not possible to become an integral domain as a field. Are you understanding that? Every field is integral domain. Every field is an integral domain, but every integral domain may not be a field. How we can prove that? I can prove with an example. We know that the set of integers z plus dot is an integral domain. We know that what is z? Integers minus 3, minus 2, minus 1. 1 minute. I will. Okay, I have corrected it. Z is equal to minus 3. What is integer set? Z minus 3, minus 2, minus 1, 0, 1, 2, 3. Is not a field. How we can say that it is not a field? The third bit is fails. What is the third bit of the field? If we go to the previous definition, third bit. Every non-zero element in that set has multiplicative inverse. Is it possible in this set? Where I am taking a 3 is a non-zero element. Is it clear? 3 is a non-zero element in Z. 3. What is the multiplicative inverse of 3? 1 by 3. We know that 3 into 1 by 3 is equal to 1. That means 1 by 3 is the inverse of 3. But that inverse 1 by 3 is not in Z. Is it right? So inverse not exist. That means multiplicative inverse not exist. The third bit fails. That means in the field definition, third bit fails means that set Z is not a field. So we say that every integral domain may not be a field, because some in university question paper sometimes questioning like that prove that every field is an integral domain and also prove converse is need not true with an example. That means converse means the reverse part. Every field is an integral domain, and the converse, that means integral domain may not be a field. You have to prove that with an example. That's why I have explained this one, and I am giving the notes this one also for you. If the converse is asked in the examinations, you can answer it with this help, with this material help. Okay, right? With the help of this material, you can definitely answer the converse part also. Okay, right? What we have proven? Every field is integral domain, and every integral domain may not be a field. But there is another theorem. But every finite integral domain is a field. Every integral domain may not be a field, but every finite integral domain is field. Are you understanding that? Every finite integral domain is a field. If we take a finite set as an integral domain, then it must be a field. We have to prove like that. For that, I am taking that. Suppose 1 minute. A small correction is there. Okay. Suppose R is equal to A1, A2 and so on An with n distinct elements is a finite integral domain. It is a finite set containing n elements. The finite integral domain with n distinct elements. That means all these are different elements. I am taking a non-zero element A. A is not equal to 0 in R. Because R is a integral domain, that means R plus dot is an abelian ring. Abelian ring means that is a ring. Ring means for that closure law exists. That means A1 is in R, A2 is in R, and so on. AAN is in R. A small correction, I have written it wrongly. It is a is an element in R, A1 by closure law, A1 in R, A2 in R, AAN in R. All these are elements in R by closure law. I have a small doubt that is there any two elements are equal? No. For that, I will want to prove it. For that, I am taking, if possible, let two different elements, AAI is equal to AAJ are equal. Two different elements, AAI is equal to AAJ. For I is not equal to J. Suffixes are I, J are not equal. That means here we take I replaces with 1, A1, J replaces with 2, A2. A1 is equal to AA2. These are the two different elements. Just like that. Just now I am taking with numbers and explaining with numbers only for the reference only. Here we are taking AAI is equal to AAJ for I is not equal to J. That means AAI minus AAJ is equal to 0. Now by the left distributive law, it can be written as A into AI minus AJ equal to 0. If we reversely see that left distribution, if we done the left distribution, that is theorem 1 third bit in this topic, AAI minus AAJ. Okay, like that. That's why we have written like that. Right. Here it is looking like AI minus AJ totally considered as B. A, B equal to 0, A dot B equal to 0, like that. But R is integral domain. That means R is integral domain. Integral domain means 2 bits. R is abelian ring. R has no zero divisors. I am using the second bit. R has no zero divisors. What is that? If AB equal to 0, either A equal to 0 or B equal to 0 is the no zero divisors definition. Now here AB equal to 0 format is there and R has no zero divisors. That means one of these two may be 0. Either A equal to 0 or A minus AJ equal to 0. But A is not equal to 0. We have taken it. Are you following the cursor? We have taken that A is not equal to 0. Therefore, the only possibility is AI minus AJ equal to 0. Okay. Right. That means AI is equal to AJ. That means two A's are equal. Here if we see that all A's are different. All A's are different. But here we get AI is equal to AJ. Two A's are equal, which is contradiction to R has n distinct elements. So this is wrong. That means any two of these elements, AA1, AA2, and so on, AN, all are different, and any two elements of these are not equal. All are different in R. That means therefore AA1, AA2, and so on, AN are all n distinct elements in R. Now I am using the pigeon hole principle. You have already learned the pigeon hole principle in the previous year, that is second year in the third sem in the group theory. What is the pigeon hole principle? I have already explained, and I am trying to explain it. If every object has a capacity of taking of one element, then every element only occupies only one object. This is the basic fundamental principle of pigeonhole principle. I am using that only for that. By that principle, all these are the A1, A2, AN. If you following the cursor, top side, you can see that A1, A2, R is equal to A1, A2, AN. All these are the objects, and AA1, AA2, AN are all the elements. These elements are occupied in these places by taking only one place. Each element takes only one place. It may be any one of these. A1 may sit in A1 or A2 or AN, and that means A1 replaces A1 or A2 replaces A1, also and so on. AN also may also replaces A1. That means there is a chance of in these elements, any one of these elements may replaces with any one of these elements, but there is only one element replaces one object. Okay, that is the fundamental principle of the fundamental behind the pigeonhole principle. Okay, right. By using that principle, every element of R is in the form of AI. Every element of R means R has elements A1, A2, and so on. Each and every element can be written as in the form of AA, AAI. For some, AI belongs to R. Okay, right. And we have A belongs to R. A belongs to R. That means A is in the form of AAE. For some, AE belongs to R. What is R? R is integral domain. Integral domain means R is abelian ring. R is abelian ring. First bit. Abelian ring means abelian law exists in R. That's why AAE can be written as AE into A. AB is equal to B type. AAE is equal to AEA. That means A is multiplying with A. We got A. A is multiplying on the left side of AE. Then we got A as this. That means AE acts as the identity. Is it right? That means that AE is called unit element or identity element in R. I am taking another element B in R. Just we say that every element of R is in the form of AAI or AAJ, AAK, AAE, whatever it may be. Similarly, B is in R. That's why B is in the form of AAK. For some, AK belongs to R. AAK are in R. R is a integral domain. That means abelian ring. By abelian law, AAK may be written as AKA. Okay, I am taking it as a 2. Now, I am taking AE into B. AE into B. I am replacing AE is as is. I am replacing B with AAK. AAK. All the elements are in R. By associative law, we can rearrange it. That means AEA into AK. What I have written? AE into AAK as AEA into AK by associative law. What happens to AEA? If you go to the previous step, what is AE into A? A. Is it right? Are you following the cursor downside? The last line, AE into A is A from 1. Is it right? That's why I have written AEA is A. AK is as it is. What is AAK from 2? AAK is B. AAK replaces B. What we have? AE into B is equal to B. Similarly, B into AE, because R is abelian. AEB can be written as BAE. Now, if we observe that B is multiplying with A, B comes out. Is it right? That means AE is unit element. Again, we have proved that AE is 1 is the unit element in R. That means we want to prove R is field. R is field means we have to prove in the definition 3 bits. The first bit we have taken finite integral domain. That means first bit is same. So we don't want to prove the first bit to prove field. We want to prove the second bit, that is R has unit element, 1 belongs to R. Now we proven that 1 belongs to R. Is it right? Now we are going to prove third one. That means every non-zero element in R has multiplicative inverse. Now we are going to prove that one. Because 1 is in R, that means each element in R is in the form of some AA. That's why 1 is in R. So 1 can be written as A into AS. For some, AS belongs to R. AS. These two elements are in R. R is integral domain. That means by abelian law, AS can be written as ASA. If we observe that A multiplied with AS, we got identity element. That is unit element. Is it right? That means AS is called inverse of A. Is it right? AS is called inverse of A. But what is the operation here? Dot. That is multiplication. That means AS is multiplicative inverse of A. What is the inverse of A? AS. What is A? A is a non-zero element we have taken firstly. Are you observing the cursor? A is a non-zero element we have taken. Now we prove that A has inverse AS. That means non-zero element has A has an inverse AS. Therefore, we have proven the third bit also. That means R is field. Hence, the theorem is every finite integral domain is field was proven.